Hey guys, Alexander here, and in this video we will be discussing the discrete random variables as well as the discrete probability distributions that will be covered in the probability theory playlist. So let's start off with discrete random variables. What is the probability mass function? The probability mass function is a function that captures the probability that the random variable x, so random variable x, takes on the realized value of lowercase x, and we often use p of x to denote the probability mass function. It's important to note that capitals such as x or y are often used to denote a random variable, and that lowercase values of those capitals denote the specific value that the random variable takes. Okay, so don't confuse it. Capital X is a random variable. Lowercase x is a realization or a value that the random variable takes. So the probability mass function has two very important properties that you need to know. The first is that since it generates or it corresponds to a probability for each realized value of the random variable, and we know that a probability can only be a probability only takes values that are less than or equal to 1 or greater than or equal to 0. Okay, so that then holds the same for a probability mass function. It can only be less than or equal to 1 or greater than or equal to 0. It can't take any other values. If you see your PMF with any other value, then you know something is very wrong. Okay, and a very common thing that we need to remember is the support of our distribution, this little x element of capital X. And what this means is it's all the values that this random variable x can take. It's the entire support. So this is used to denote the entire support of the random variable x. Okay? And sometimes you'll see it shortened to just x. So if you see a summation operator and you see the summation of x px, this one is should be over here. If you see it over here below the summation operator, not next to it, if you see it below, then often they use that to denote the summation over the entire support, or the summation from starting from x is equal to whatever value. Okay, so the second property is that the summation of the probability mass function, this is the summation of the probability mass function over x element of the random variable x, all the values that the random variable x can take should be 1. And the reason for that is we know that the probability can only be less than or equal to 1 or greater than or equal to 0. So if we sum up all the probabilities for every possible realization of the random variable, we know it has to be 1, because that's all of the events. And the probability that all of those things occur, if we sum them all up, that should be 1, because that encompasses all the events that are occurring. So two key properties of the probability mass function is, remember, each value of the probability mass function cannot exceed 1 and it cannot be less than 0. Remember as well that the summation over the entire support of the probability mass function should equal to 1. So the next thing I'd like to cover with you is the cumulative distribution function. It's a function that captures the probability that the random variable x is less than or equal to some value lowercase x. So it's less than or equal to some value. So it's the probability that the random variable is less than or equal to lowercase x, which is a realization or some value. Okay. The formula for that is the summation of all these values that are less than or equal to some value of interest y of the probability mass function, which is equal to, which we then sum and we get this to be that function. It's the f of a, capital F of a. That denotes the cumulative distribution function. Now, some of the distributions you'll encounter have closed form solutions for them, some of them don't. So I advise you to go and look up the distributions as you're going through this playlist, and see what are the cumulative distribution functions. See if you can work them out by your own working, or look up what the cumulative distribution functions are, because you will be asked to calculate or use this CDF in many of the questions that you will encounter in your studies. Okay, so the important properties of the cumulative distribution function is that it is a non-decreasing function of x. Well, why is it non-decreasing? Because we're adding probabilities. It's like taking a chunk of probability, adding another chunk of probability to it. Maybe we don't have any other probability, but we keep adding and we keep adding. And since the probability mass function, because we're summing over the probability mass function, we know the probability mass function is always has a value that's greater than or equal to 0 or less than or equal to 1. So since it's greater than or equal to 0, we know that it's going to be non-decreasing if we sum over it, because you can only add 0. If you add 0, it's not going to decrease your value, it will keep the CDF's value the same. If you add anything greater than 0, it will increase. So the cumulative distribution function is a non-decreasing function of x. Okay? And the limit as x goes to infinity for the cumulative distribution function is 1. And all that means is, once you've covered the entire support of your distribution, you know that all the probability that the random variable will be less than or equal to that highest value is going to be 1. Let's go to some important results: the expected value and the variance. Now, the expected value of x for a discrete random variable is the summation of x over the entire support of the lowercase x times the probability that that realization occurs. So it's the summation of x times the PMF of capital X, okay, which we note and denote as P of x. That's the definition of the expected value for a discrete random variable. Remember this, because this result is crucial. You need to know this. And note too that expected value is synonymous with the idea of the mean of the distribution. What is the mean of the random variable x? Well, it's the expected value. Okay? So the variance of the random variable x is the summation over the entire support of x subtracted from its mean squared times the probability mass function of x. Okay? And note there's a shortcut formula for this. Variance of x is equal to the expected value of x squared minus the square of the expected value of x. And I will show you now how we derive that result, but memorize this result because it will make life much easier for you when you are trying to derive various results or find the variance of random variables. So let me show the result for the discrete case. So we know that this formula holds the variance of x is equal to the summation x element of all the realized possible values from x minus the expected value of x squared times the probability mass function of x. If we expand that bracket squared, then we end up with x squared minus 2 times the expected value of x times x plus the expected value of x squared. And all of this multiplied by the probability mass function of x. If we go and simplify further, we see that we end up with the summation of x element of x squared px minus 2 times the expected value of x times the summation of all values. I will just use a short single x to denote that, the lowercase x, of x px plus the expected value of x squared, the square of the expected value of x, times the summation of x p. So p of x, the probability mass function of x. Now, in my discussion about the probability mass function, I already gave you the result that this summation over here, we use a different color, this summation over here sums to 1 because we're summing over the entire support of the probability mass function. So this right-hand summation results in the expected value of x squared. This summation over here, this is just a definition of the expected value. So we have negative 2 times the expected value of x squared. And over here, the summation of x squared px, well, this is simply the definition of the expected value of x squared. This is the expected value of x squared. This is the square of the expected value of x. And this is the square of the expected value of x squared. So we have the expected value of x squared minus 2 times the square of the expected value of x plus the square of the expected value of x. And we know that this simplifies to the expected value of x squared minus the square of the expected value of x. And voila, there we have our results. We have the result for the variance of the discrete distribution, or the variance for discrete random variables. And this formula also holds for continuous distributions. Its derivation is just slightly different, but it follows along the same lines. Now I will proceed to discuss the discrete probability distributions that we will be covering in this probability theory playlist. The main types that I'm covering are the Bernoulli, which represents the outcome of a flip of a coin, but these are the analogies that I'm going to use to introduce them to you. A Bernoulli distribution is like flipping a coin and looking at the outcome of that flip. A binomial distribution counts the number of heads in flipping n coins. So it's related to the Bernoulli distribution, and that's why I've colored both of them in blue, because the binomial distribution counts the number of heads in flipping n coins in n independent trials that are each Bernoulli distributed. The geometric distribution counts the number of flips until our first heads appear. And that's related to the negative binomial distribution, which counts the number of flips until our heads appear. So both of these are kind of like brothers in the sense that the binomial distribution is going to be counting a bunch of Bernoulli distribution. The negative binomial distribution is going to be counting a bunch of independent, identically distributed geometric random variables. So these are related to each other. And that's why I've colored them in this manner, so that that association can form in your mind. And lastly, I will be covering the Poisson distribution, which we use to model the rate of arrivals of events in a unit of time. So the rate of people arriving at a shop, the rate of buses arriving at a bus stop. Thank you very much for watching. I hope you've enjoyed this introduction of the discrete random variable as well as the discrete probability distributions that we will be watching. I hope you're enjoying this playlist, and I hope it can be of benefit to your studies. Like and subscribe if this video was beneficial to you, and please do ring the notification bell so that you can receive notifications when I upload a video. Thank you very much for watching. Boer Commander out.